Pluto is a distant and mysterious dwarf planet that was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets, which could be a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects such as Pluto, Neptune, and the Sun move and affect each other with their gravity. It's like trying to predict their paths based on their initial positions and gravitational interactions. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms alpha libration, latitude libration, and the VZK oscillation are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune, or any other giant planet, it is situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zippel-Lidov and Kozai, who studied how celestial bodies move in space. This oscillation describes how Pluto, Neptune, and the Sun influence each other, gravitationally affecting Pluto's unusual path around the Sun. Even though Pluto's path seems erratic, this oscillation helps maintain long-term stability. These components ensure Pluto's orbit remains stable, preventing it from crashing into Neptune or being thrown off course. The three-body problem helps us understand how gravitational forces influence celestial paths, revealing broader insights about our solar system and distant worlds. Numerical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions could lead to significant changes over millions of years. However, these unique orbital characteristics have been found to maintain stability over incredibly long time scales, effectively keeping chaos at bay. Recent computer simulations have provided more insights into how giant planets like Neptune, Jupiter, and Saturn affect Pluto's trajectory. Neptune has a special connection with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps keep Pluto's path stable. But Neptune isn't alone. Jupiter's gravity also plays a major role in keeping Pluto's orbit safe, and Saturn contributes as well. These simulations show that Jupiter's gravity alone is strong enough to keep Pluto on a stable path for billions of years. In essence, Neptune, Jupiter, and Saturn work together to ensure Pluto continues moving safely in space. These gravitational phenomena are essential in maintaining order in the solar system. Without them, space would be far more chaotic, with celestial bodies potentially colliding or being ejected from their paths. Understanding Pluto's orbit is crucial, especially with discussions about a possible future collision with Neptune. This study provides valuable insights into the dynamic nature of our solar system. Pluto's case demonstrates how even seemingly unstable orbits can achieve equilibrium through complex gravitational interactions. It also highlights the importance of continuous observation and research in astronomy. The concept of orbital chaos, the sensitivity of a celestial body's trajectory to initial conditions, is vividly illustrated by Pluto. Even slight variations in Pluto's position or velocity could significantly alter its long-term path. Since its discovery in 1930, Pluto has been extensively studied, leading to major revelations about its composition and behavior. One of its most fascinating features is its surface, which is a complex mix of ice, rock, and various compounds. NASA's New Horizons mission, which flew past Pluto in July 2015, provided unprecedented data. Pluto's surface is characterized by vast plains, towering mountains, and deep valleys. One of the most notable features is Sputnik Planitia, a massive heart-shaped plain primarily composed of nitrogen ice. This region contains large icebergs and apparent flowing glaciers, suggesting that Pluto may still be geologically active despite its distance from the Sun. Pluto's thin atmosphere, mainly composed of nitrogen, methane, and carbon monoxide, also exhibits seasonal changes. As Pluto approaches the Sun, its atmosphere expands, and as it moves away, gases freeze onto the surface. Pluto's interaction with its largest moon, Charon, adds further complexity to the system. Charon is nearly half Pluto's size, creating a mutual orbital system rather than a traditional moon-planet relationship. This interaction influences not only Pluto but also other Kuiper Belt objects. The Kuiper Belt, located beyond Neptune, is home to many other dwarf planets. Studying Pluto's orbit provides clues about the migration patterns of these objects, offering a window into the early solar system. Understanding Pluto's orbital dynamics helps scientists uncover patterns in planetary evolution. The gravitational pull from Jupiter and Neptune influences smaller bodies like Pluto, sometimes altering their orbits over time. The classification of Pluto as a dwarf planet in 2006 remains controversial, sparking debates about what defines a planet. This ongoing discussion reflects our evolving understanding of celestial bodies. Future missions to Pluto and the Kuiper Belt could provide more insights into planetary formation and even the origins of life. As technology advances, scientists hope to explore Pluto further, uncovering more secrets hidden in the depths of space. Pluto continues to captivate scientists and the public alike, symbolizing the endless mysteries of our universe. As technology advances, scientists hope to explore Pluto further, uncovering more secrets hidden in the depths of space. Pluto continues to captivate scientists and the public alike, symbolizing the endless mysteries of our universe. As research progresses, we move closer to understanding not just Pluto but the fundamental forces shaping the cosmos.